think for that one. Okay.
Times and
Examples of projectile
concerts are synonymous, but for this DJ, his good times came to an end from what we hope will be his last stage dive. The object here is to run, dive, and be caught by the concert goers. Well, he ran, he dove, but no one got around to catching him. Fortunately, he lost only consciousness.
All right, so that's one example of projectile motion.
Inches from the bottom of your screen. That line is where envy stops. You're thinking about throwing someone in the pool. Make sure there's one there.
For example. She did not seem that she enjoyed the impact. Did she? Fourth example. So trajectory of a golf ball, projectile motion. Cubic arrow is projectile motion. Bombs, projectile motion. Whenever the adductors are operating on you, when they pull out the internal organs and squeeze them really tight, trajectory of those organs is also projectile motion. Here's your mind twister for the lecture. All right. Take all the time you need and study this carefully. I'll give you guys one more second. Thumbs up. I notice that he's holding a bullet, she's holding a rifle, same height. All right, so she will pull the trigger, so the bullet is going to be projected forward, parallel to the ground. So it's going to get fired forward, parallel to the ground. So the question is, which bullet will reach the ground sooner? The one that he drops, she fires, or both at the same time? What do you guys think?
I think the same time.
Okay, Jack, you're thinking that it's going to be the same time. Why did you say that?
Yeah, because I mean, even if there's projectile motion acting on the bullet, they'd just be pushing it forward, not up. So gravity would be affecting them the same. So they'd be accelerating downward at the same rate.
Okay, so Jack, I'm gonna give you 10 points for the explanation. Okay, guys, let's go with common sense. I know Jack claims, justifiably so, that he says gravity is the only force acting if you ignore air friction. So we know from last week that if gravity, under the influence of gravity, everything falls at the same rate, right? So what Jack is saying is, regardless of how fast this may be moving horizontally, it's still going to fall at the same rate. So what that means is this horizontal speed should not matter. Okay, both of them should land at the same rate. The prevailing commonsensical idea is, hey, this is shorter, this is just going to fall, and this thing is going to travel maybe half a mile, maybe a mile. There's a tremendous amount of force behind this bullet. In fact, if you're standing in front of this rifle, it's probably going to kill you. All right, so to you, it doesn't make sense that they should land at the same time. You can argue, in fact, most people will argue with you endlessly that this bullet lands before the bullet which is being fired. So we'll investigate. And before we do that, let's talk about animals. All right, so some of you guys like dogs, some of you guys like cats, and some people actually love monkeys, right? Let's imagine that you love monkeys to an extent that you volunteer at a zoo. You're taking care of a monkey. And then one day you show up for work and your boss says, hey, your monkey, the monkey that you're in charge of, has escaped. They want you to go out and capture the monkey. And your first question is, how is that even possible? How is it that the monkey escaped? And they have a story for you.
It's kind of like that. Sierra Mist. Taste one shockingly refreshing lemon lime.
So what do you need in order to capture the monkey? Sierra Mist? No. Bananas? They're not that stupid. They're not going to come back. So what you need is a tranquilizing gun, right? Tranquilizer. Instead, this dude doesn't have a tranquilizing gun. They have a tranquilizing cannon. All right, so you go find the monkey. It's hanging from a branch of a tree, and you're about half of a field away. This is like 50 yards. All right, so you will fire the cannonball to hit the monkey, except the cannonball is not going to go so fast that you will kill the monkey. It's going to go fast enough to stun the monkey, if you can hit the monkey. Except here's the catch. When you fire the cannonball, it's going to make a loud sound. It's going to go boom. Monkey's going to get scared. So he's going to release his grab. So as soon as you fire the cannonball, the monkey's going to go in a free fall. So if that's the case, where would you aim in order to hit the monkey? You got three options. You can aim above the monkey, at the monkey, or down below the monkey. What do you guys think? Above, at, and below. Fire the cannonball, monkey goes in a free fall. So where would you aim in order to hit the monkey? Above, at, and below. What do you guys think?
It depends on the distance.
It's how most people watch football here. It's half a football field in length. That's 50 yards. I'm going to give you 50 yards. All right, hold on. We got a bunch of people saying a bunch of stuff. Let me just find that. All right, I'm trying to get to you. All right, so it's going to be 50 yards. I can't get to you guys. Oh, finally, chat just opened up. Okay, I see a lot of people saying below. Okay, cool. So let me ask you this question. How far below are you guys looking, aiming? Are you thinking that you should aim right at the balls so you can hit them right in between the eyes? Is that what it is? All right, so we'll get back to that question. All right, so according to physics, ignoring the effects of air friction, the bullet dropped and the fire from the same height should reach the ground at the same time. So ignoring the effects of air friction, the only force acting is gravity. So what does gravity do? Gravity makes things fall at the same rate. So everything is going to fall at the same rate. Regardless of their weights, sizes, the shapes, according to what we were discussing last week, everything still falls at the same rate. This week, we're adding on to it. We're saying, hey, regardless of their horizontal motion, things will still fall at the same rate. So it doesn't matter how fast this thing is moving horizontally. It's still going to fall under the influence of gravity. It's still going to fall at the same rate as this will. So what that means is projectile motion is also free fall. Remember, free fall is the motion under the influence of gravity and gravity only. Projectile motion is free fall. It's a form of free fall. So regardless of the speed of this bullet, it doesn't matter how fast the bullet is projected or fired, both bullets will still fall at the same rate. That's according to physics. That's what we expect to see. Is it true though? Let's find out. Mythbusters actually did this experiment. Here's what they came up with.
Was needed to match the solenoid. All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet drop versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone. Wow. And the results are simply ripping.
Can't get much closer than that. Oh, I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened. Until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Okay, so 39 milliseconds.
So after days of brain-teasing,
the difference is 39.6
So the fired bullet landed 39 milliseconds later.
milliseconds.
That's 400th of a second.
Which means it's less than the human eye can make out.
You're not going to be able to see it, but the facts are undeniable. So you expected the drop bullet to land first, and the drop bullet landed first. According to physics, they were supposed to land at the same time. Does this mean that physics is wrong?
No, there would have been air resistance in this experiment.
Okay, so that's, I'll give yourself 5 points for that one. That's called experimental error, guys. Something about life which is kind of mystical. Nothing is perfect in life. The experiments are not perfect either. There's always something called experimental error. Those of you guys who watch this episode will recall that we spent a lot of time reducing error, time after time. That's the best that we were able to come up with. So the question is, what caused the experimental error? How about the time spent inside the barrel? All right, so the bullet was not projected immediately. It's a bit of a time spent inside the barrel. On top of that, the bullets, when they're fired, they spin, just like the football does, thrown by a quarterback. So why do the quarterbacks throw while spinning the ball? Because the ball, in essence, gets a little bit of a lift because of the spin, right? All right, so you got a spinning bullet. There's the effects of air friction and time spent inside the barrel. So it just adds up this experimental error. As a result, the bullet actually landed within 400th of a second after the drop bullet landed. That's known as experimental error. So we'll say that both of them landed at the same time. All right, so that's actually pretty damn good. So what do we know? We know that in the absence of air friction, all objects will fall at the same rate of acceleration, otherwise known as free fall. And once again, in the absence of air friction, regardless of their horizontal motion, everything still will fall at the same rate. So projectile motion, in essence, is the same as free fall. All right, guys, put down your answers in the chat. Okay, very good. I see a lot of C's. So Drills has 5 points. So both bullets will just run at the same time. All right, so here's a multiple flash photography on the left-hand side. So red and yellow is projected. Notice that following the same distances along the y direction within the same time period, so that's free fall. And there's supposed to be a simulation that I did working out on this PowerPoint for some reason. Okay, so moving forward. Free fall, projectile motion. Along the y direction, notice that it's gradually speeding up. Okay, so you're looking at the projection of the ball along the y direction. Along the x direction, I want you to notice that the distances within the same time periods are fixed. So it means that the motion, horizontal motion, is happening at a constant speed. So speed is going to be constant horizontally, so there's no acceleration along the x direction. So we got 0 acceleration along the x direction. Along the y direction, the acceleration is the same as the gravitational acceleration. So we got a little bit of an insight to the projectile motion. So now we can do a bit of a mathematical modeling of it. So this week, motion is 2D, two-dimensional motion. We'll take a look at 2 topics. Today's topic is going to be projectile motion. All right, so you got the x direction, you got the y direction of this motion. Projectile motion is going to give you a parabola. Notice that the motion starts at initial velocity, so VO is your initial velocity. At an angle, so theta naught is going to give you your initial angle. This is known as the range of motion, so this is the distance along the x direction. All right, and then as this is moving along the x direction, it's going to go up and it's going to come back down along the y direction. So, all right, so this is the amount of time it's going to take for it to actually cover this range, and it's the same amount of time for it to go up and come back down. So just I want you to remember the time along the y direction, the total time along the y direction will be the same as the total time along the x direction. So they will be common to each other. So this is a vector, which means that it's going to have 2 components. It's going to have an x and the y component. And projectile motion is going to have a final speed here. Okay, so once again, it's going to have 2 components on the x and the y directions. So it's a vector, so which means that from these 2 components, you can figure out the final speed. Okay, now this is starting off physics this fashion, this is into mathematics or into the mathematical realm. It's a little bit too complicated for most students. So here's what I'm going to do. I'm going to ease you into it. So what I'm going to do is, instead of looking at the full projectile motion, today I just want to focus on half of it. This is known as sideways projectile motion, mathematically. So we can ease you into it. So which means that motion is going to start at the top of this trajectory, and it's going to be only sideways. Okay, so along the vertical direction, along the y direction, the velocity's initial speed is going to be 0. So I'm just moving my y-axis towards there, and then we're only going to look at this portion of it. So sideways projectile motion is an easier version of it. So mathematically, I want to kind of ease you into physics of it. All right, so these are the free fall equations. So if we are looking at the sideways projectile motion, there's no initial speed along the y direction. All right, so the initial speeds will go to 0. So these equations will be reduced to these 3 equations. All right, so let's stop at this point and then have a quick discussion going. All right, these are free fall equations. You know the time, you know the distance followed. You know the time, you know how fast it's moving at that time. You know the location, the vertical location, you know how fast it's moving at that vertical location. These are free fall equations. These are simplified free fall equations. Now, along the x direction, believe it or not, motion also has a uniform acceleration. All right, so once again, the motion is 100% predictable along the x direction. There's a slight catch. All right, so once again, we got 3 uniform motion formulas, except acceleration is 0. Okay, so along the x direction, when the object is airborne, like this ball is, horizontal speed, unless you're pushing or pulling on it, there's no reason for it to speed up or slow down. So the horizontal speed is going to remain constant, which means that there is no change in acceleration along the x direction. So which means that these a's will go to 0. Immediately, we will get simplified 3 equations. I want you to notice that this equation and that equation, these 2 equations are the same, right? If you square both sides, this is what you get. So the last equation is redundant, so I'm just going to get rid of that. All right, as a result, describing sideways projectile motion, we will get to use these 5 formulas. That's it.